Can you hear me, class?
Opo, sir.
Okay. So for today, we're going to discuss our module 2, no? The, of course, storage system, no? Specifically when it comes to a storage models and disk. So, storage models, no? Describe the layout of a data structure in physical storage. So a data model captures the most important logical aspect of a data structure in a database. And the physical storage can be a local disk, a removable media, or a storage accessible by a network. So the two abstract model of storage actually, okay, so is the cell storage and journal storage. So cell storage assume that the storage consists of cell of the sample at the same size and that each object fits exactly in one cell. And these models reflect the physical organization of several storage media, and the primary memory of the computer is organized as an array of memory cells, and the secondary device is organized in structures or blocks read and written as a unit. Okay, so I'll just want to share my screen. Okay, so as I mentioned earlier, now we're going to discuss the storage models, and this will be our module 2. So errors, no, without a clear cause are the most irritating problems to deal with. And while Linux is usually specific in its error messages, this is one of the few times when it drops the ball. So getting a no place left on drive on device error. It explains very little, no, especially if your device or even your drive is far from full, no. Why is this error message showing up? So why can't you create new files despite having sufficient space on the disk? And most importantly, how do you fix it? So before you rush to find a fix, make sure there is a problem to begin with. After all, if this space has actually run out on your system, there is no need to panic. So you can just remove unnecessary data to free up more space. Okay? So there are two Linux system commands for getting information about this space. So we have du and df. No? So the du command estimates the disk space usage, while the df command analyzes the free space present on the disk. So using them in conjunction with sudo gives you an accurate report of how much space is actually available on the disk. So let's start with the du command. So as what we have here, no? Its output can be rather long and cumbersome to go through. So we will use the -s and -h flags. As you can see here, now we use -sh. No? It summarizes the result, while das, of course, -s summarizes the results, while -h ensures it is human readable. So when we enter the command sudo du -sh/, where slash points the base directory. No? So this slash is the base directory. Again, du, no? Sudo du -sh. S or -s, okay, summarize the result. -h, no? Ensure it is a human readable. Okay? Now, don't worry about all the permission denied messages. No, kasi makikita nyo rito, denied, permission denied, permission denied. So once we enter that sudo do dash sh, ito yung makikita natin. No? Now, because that's how it trolls through all subdirectories of the system. Depending on the size of the drive, you may have to leave it running for a while as it recursively goes through everything. Then, when DU finishes scanning, it will output a simple list of directories alongside their sizes. So, for example, this is the output of the DU command applies to an ordinary directory. No? So you have a 4.0K examples. No? And now we will use df to see how much free space is available. So the df command is much simpler to use since it only shows the mounted file system and their usage statistics. Once again, we will use the -h flag to make the output human readable. So sudo du-h. So as what we have here, we use sudo.df.h. So the idea is to tally the results of the du and df commands. Okay? So any discrepancy points to this space that is not freely available despite not being used by any files or folders. Okay? Do you have a Linux subject before, or you already finished with your operating system? Done na po ba kayo sa operating system, or do you have an idea already about the Linux command? Hello?
Wala pa po, sir.
Oh, wala. So you mean to say you don't have operating system subject?
Meron sir pero hindi na-discuss yung about sa Linux command.
Okay, so
Hindi po mama.
okay, thank you. So what you're going to do, of course, is to look for a tutorial, on how you'll be able to understand the sudo specifically for Linux, and we have already given commands, especially the -h, -s, df, du, and of course, if you are seeing the no space left on device, error message despite having sufficient free space on your disk, it's not the hardware that's at fault. Figuring out the exact cause for the error can take a bit of troubleshooting. So we have, of course, the recently deleted file. The most common reason for seeing this error is a recently deleted file. Now, open a file is deleted while a process is still using it. So keeping the space reserved even though the file is already gone. Minsan ganun So even we deleted the files, still, kasi minsan naka-open pero dinilit mo siya, It happens, So another is not enough nodes or not enough inodes, Okay. Another frequent cause is not having enough inodes or inodes, Inodes are the index pages of a Unix file system holding the metadata of every file on storage. However, inodes aren't unlimited, and running out of inodes before the storage space can give you the no space left on the device error. So another is the falling hard drive, Mag-accept. Sinong pwedeng mag-accept? Okay. Then falling hard drive, then of course there is the possibility that the hard drive is simply failing, and much of the apparent free space is taken up by bad sectors. Since the system fails to write any files to this location, it throws an error. Okay. So as what we have here, we had a recently deleted file. It caused, of course, for the common error saying in a recently deleted file, not enough inodes, as I mentioned earlier, and at the same time, failing hard drive. Okay? So how we'll be able to fix? Number one, restart processes using deleted files. Okay? So as what I have here, no, sudo, no, lsof, no, slash, then yung grep deleted, no. So the most probable cause of the no space left on device error is process is still using a deleted file, as I mentioned earlier, no. So thankfully, fixing this error is easy. Okay? You just need to restart the process to free up the reserved storage. So most commonly, no, especially during our basic, no, in the introduction or system fundamentals, our professor shares, no, on how important refresh, no, the refresh command or F5 command, because let's say for example in a room and RAM, we RAM is the random access memory, no, wherein anytime na mag-open ka ng file or files or documents, automatic yung memory nun pumupunta kay RAM. Okay, let's say Microsoft Word, PowerPoint, YouTube, social media like Facebook, Instagram, same with you also open Adobe Photoshop, or sometimes you also open Python programming at the same time. So it happens na kapag marami na tayong nadalang na open na files or documents or software applications, lahat yon pumupunta kay RAM, bumabagal. Then there are certain cases, no, ang ginagawa natin doon, nag-close tayo ng applications. But still, bakit mabagal? Doon gumagana si F5 or si refresh. So even na-close na natin yung applications, but hindi tayo nag-refresh or nag-restart ng computer, still, mabagal pa rin yung ating computer. Okay? So, the lsof command, no, this one, no, the sudo lsof command, no, will give you a list of all open files being used by running processes, and grep can narrow down the selection to the ones that are deleted. So you need to enter the sudo lsof slash, tapos yung ating yung ginagamit natin for or for not, no, grep deleted, no, where is slash is the base directory, and this one is a pipe, no. Ito pipe ang gamit nito for linking lsof's outputs to grep. Now you can restart the affected process, no, with the sudo systemctl. Okay, ayan na po, systemctl, then restart service_name. So kung ano yung pinaka-name niya, command, no. So where the service, no, name is the name of the service that turn up in the search, no. And now you can restart the affected process with the sudo systemctl restart service_name, no, where the service name is the name of the service that turned up in the search, as I mentioned, no. After this storage space being held up, no, by the process, it should be available again, allowing you to write files without running into any errors. Now, next will be, of course, check the inodes, no. While each drive has a large number of inodes or inodes, it is finite, no. And if your system is littered, no, with an incredible number of files, it is possible to reach with this limit before exhausting the storage capacity of the drive. Now, this is why it's better to have large files rather than too many small ones. You can easily check the availability of inodes by using the -i flag with the df command, like this, no? Yung ating inaano na sudo df-i, no? This one, no? Sudo df-1. This will clearly tell the total number of inodes present in the file system, along with the amount currently in use. So if there are no free inodes left on your system, this is the source of the no space left on device error. As inodes are only created upon first formatting the drive, there is no way to generate more inodes. All you can do is delete any necessary or delete any unnecessary files to free up inodes for future files. Data corruption, no, is the inevitable fate of any hard drive. So, while a new drive will not run into this issue, older hard disks will gradually start going bad. Siguro kayo, ang dami nyo mga hard drive na hindi na ginagamit kasi may problem. No? What this means is that portion of the hard drive are rendered unusable. No? Even though the file system is still considering them functional, these bad blocks falsely inflate the apparent free space on the drive, when in truth, no files can be written on them. And this leads to a no space left on device error, as the operating system tries and fails to store any data on this location. Actually, there is no real way to fix this issue, no? But as bad sectors are a result of the physical wear and tear of a hard drive, the only thing you can do is mark the bad sector so that they are no longer referenced by the file system. Doing this requires you to boot from the live CD, as you cannot perform a file system check within a running drive. No? Once you do that, just use the following command. Ito lang gagamitin natin. Sudo, online po, gamitin yung live CD, no, na online, no, sudo fsck -bcck /dev/sda, because this replaces the /dev/sda with the path of the device or with the path of the drive you want to refer, and this will automatically detect all bad blocks on the drive and mark them as unusable. So it won't give you any extra storage capacity. However, so be prepared to clean up some useless files to free up space on the drive, no? So lahat naman may laptop, no? Pwede ng dual booting. Lahat ba may laptop? Or cheer na eh, no? Possibly lahat may laptop. Lahat ba kayo may laptop? Pwede sa dual booting? Lola yata nakikinig.
Yung iba po ata, sir. Wala
Yung iba
po.
naka-Linux na. Okay, try to look, I think try to install, of course, Linux and dual booting, no? Kasi we have an activity wherein you are required to perform some available activities with guidelines, no? Kasi nga po wala naman tayong face-to-face. Ako hindi ako makakapunta, no? So ganun mangyayari sa atin, okay? So I will send actually a video presentation wherein you could able to have yung partition, no? I think may idea naman kayo dyan, especially you are a fourth year student, no? Okay, so the usual reason for seeing a no space left on device error on actually if you are using Ubuntu, no, as your operating system, no, or any other Linux distro, is a deleted file is still being used by a running process, and this reserves the storage that was occupied by the file, preventing other operations from writing data to the space. And fixing this problem is also the easiest, as all you need to do is to restart the process in question. So the other causes of the error, however, are not that easy to solve. Okay? So whether your drive is flagged, no, by bad data, blocks, or has run out of inodes, there is no direct way to fix this issue. So you must delete existing files to make room for new data to be written.
Hello, and welcome back to CS615 System Administration. As we're moving on to week 2, where we are going to be talking about storage models and file systems, I thought it might be useful to start out with a quick exercise to warm up. For this, we're going to try to follow every sysadmin's favorite train of thought. I wonder what happens if. I recommend that you use this video to follow along and run the same commands, but also to then think beyond just what you've seen and explore more. So make sure to open a terminal and play along, pausing the video as we run through this episode of Full House entitled No Space Left on Device. Let's begin by starting a new screen session. If you're not familiar with Screen or with Tmux, I recommend that you check out the tooltip video I've linked from the course website. But let's continue. We log into the Linux lab and take a look at how much disk space we have on the local file system. Looks like we have plenty of space, 11 gigs. Let's create a large file to use up all that disk space using the dd command shown here. This is going to take a few seconds, but eventually you're going to run out of space. The file we created is 11 gig large, so not surprisingly, our file system is now full, preventing us from writing any data or creating any new files. But this can have other negative side effects that may be quite a bit less obvious. With the file system now completely full, let's try to log in again. Again, we run SSH and we get some error messages. But we're still logged in, aren't we? Let's try to run a few commands. What? Nothing's working. Let's check what's going on in the other shell where we were logged in the beginning. First, let's take a look at the dev standard in, dev standard out, and dev standard er devices. They all point into the procfs, a pseudo file system representing file descriptors. Now, let's see what processes we're running. Well, this shell appears to be process ID 20115. The other shell running must then be the one that's so broken, PID 20157. So we can look at the file descriptors associated with that PID under proc 20157 fd. Here we find a few open file descriptors, with file descriptor 0 and 2, standard in and standard er, pointing to the pseudo terminal PTS36, but we notice the absence of a file descriptor 1, standard out. This explains why the commands we ran didn't produce any output. Standard out was apparently close. As it turns out, my login shell, KSH, the so-called corn shell, tries to open a few files in redirect IO when you log in, but if the file system is full, it can't do that, and we end up in an impressively busted state. So let's try another shell instead. The SSH command lets you specify a command to run when you connect. So let's run bash. Now what? No error. Are we logged in? Turns out we are. When we run a command directly via SSH, then we don't get a pseudo terminal allocated, but the command bash in this case is still connected to standard in and standard out of the SSH command. So we can run commands. Look, there's that big file we created. But we'd be more comfortable having a normal shell when we log in. So let's ask SSH to allocate a pseudo terminal for us by specifying the -t flag. There, that looks more normal, doesn't it? So apparently bash has no problem with a full file system at login time. And we can now remove that big file that we created that's using up all the disk space and caused the problems. Okay, now with that cleaned up, we can exit here. Now that the disk space that was taken up by the file temp_big has been made available again, we can check in on our connection in the broken shell, which still remains broken, because just by removing the file does not miraculously allocate a proper file descriptor for the shell we have sitting here. So let's exit that shell and reconnect. There, everything's perfectly normal again. Now if you try to recreate this scenario, please do make sure to remove any large files you create so that the system does not get negatively impacted by you playing around with this exercise. You will likely see slightly different behavior depending on whether you have bash as your login shell, but I specifically wanted to illustrate that the act of filling up the file system can have an effect on seemingly unrelated processes with possibly confusing or inconsistent results. One user might complain, while another user might not notice anything odd right away. Alright, so we've seen what happens when we fill up all our disk space with one giant file. Let's try something else. Again, let's take a look at how much disk space we have available here. And let's create a directory under /temp and specify a path name for a large file we want to work with. If we look at the output of the df command, we can extract exactly how much disk space is available from the fourth field. There. Now, we'll use the truncate command to create a file of a specific size. Specifically, we'll try to create a file that's many times larger than the available disk space. So we copy this command here and append a few zeros. There. Wait, what? We were able to create a file that's thousands times larger than the available disk space? How did that work? Look at the size of this file. It's impossible. And df even tells us that we have plenty of room to spare. This makes no sense. What does du tell us about this file? Okay, du tells us this file uses 0 blocks. What does stat say? Stat shows us the file size as being really large, but still using 0 blocks. So what on earth is going on here? The file we created clearly appears to both have a huge size and use no disk space. This is because it was created by simply setting the file size, but not by writing any data to it. It's a so-called sparse file. Not all file systems support sparse files, but this one does. What happens when you copy this file? Okay, that seems to work. Now we have 2 of these weirdo files here, both seemingly huge yet using no disk space. This is because the cp command is smart. It detects that this is a sparse file and then creates a true copy of this file. But if we try to read the file using cat and then redirect the output to another file, this suddenly takes a really long time, and eventually we get back the error that we're out of disk space. And now look at these 2 files. The second file now uses lots of blocks on disk, so many that it filled up the file system. This is because when the kernel tries to read a sparse file, it notices that there's no data there, so it supplies null bytes instead, and the reading process will then see null bytes, which in this case it writes out to the second file. Weird, huh? As you can tell, our disk is now actually full again, and only after we remove the files do we get back our disk space. So this is an illustration of surprising behavior that may depend on the file system in question. If you run these commands in some other operating system or using a different file system, you may get a different result. But alright, let's move on. We've now seen how our system behaves if you create really large files. When you actually write data, it obviously uses up the disk space. But you're also able to create a file that looks like it's huge but doesn't take up disk space. But what happens if instead of creating one huge file, you create lots and lots of small files? Let's give it a try. Here, we use the df-i command to inspect the inode usage of the file system. We'll go into much more detail in a future video segment about what exactly an inode is, but for now, suffice it to say that each file is associated with an inode. So in this case, we have 923,261 available free inodes. If we create a directory, then we've used up one inode. And if we create one file, then we've used up another inode. Likewise, if we remove the file, then we get back the inode, and likewise for the directory. Makes sense. So now, let's see what happens if we use up all of our inodes. For that, we need to create 923,261 files. That's going to be tedious if we run individual commands. So I wrote a simple program to create new files for us. You can fetch it from our course website. And it looks like so. We create a directory, and then we loop forever, creating new files in that directory until we fail. Let's compile and run this program. Okay, so after some time, the program will fail as we expect. It reports that it has created 923,260 files, plus that one directory under which it created the files. Note the error message, no space left on device. Sounds like full house, I mean disk full. Let's take a look at the size of the directory. Oops, wrong path. Over here in /temp. There, this directory is pretty large. Let's look at the files we created in there. Notice how even running ls on it takes a long time? That's because the directory is so large. Let's confirm how many files are found in the directory. Yep, 923,260 files. So now, let's try to create a new file. Nope, no can do, no space left on device. But I can move a file from the directory into another one. This is because moving a file does not create a new file. Again, we'll get into the details of that in a future video. But so the file we created is 0 bytes in size, and so are the other 923,259 files. But how can we be out of disk space then? Didn't we have 11 gigs of space available? Well, it turns out that we aren't out of disk space. We actually can still write data to the disk. So long as we write it to an existing file. We are out of inodes, meaning we can't create new files, but we can certainly still have disk space available, as shown here. In fact, we can easily write a gigabyte of data to the existing file. See? No problem. But let's clean up and remove the almost 1 million files we created here. Note again that this takes quite some time. Let's suspend the process for a second and check if we've made any progress. Yep, looks like we've freed up almost 200,000 inodes already. Let's continue. Oh, and let's also take a look at the directory size while we're removing all those files. Huh, look at that. Same size as when it contained almost 1 million files. Alright, more on that later. Let's continue for now. There we go. Back to where we started. Alright, did you run the same examples? Did you play around with what happens when we use up disk space or inodes? Here are the key things this warm-up exercise was intended to illustrate. 1. Running out of disk space can lead to odd side effects. We saw that when some users were unable to log into the system because the disk was full, but other users had no problem. 2. File sizes are not always what they seem to be. There's a difference between a file size and how many blocks of disk space a file uses, and this difference can be significant depending on the file and file system. 3. Error messages aren't always what they seem to be. When we ran out of inodes, the error message was no space left on device, but that's misleading. If you saw this error message and then ran df, it would have shown you many gigabytes of free disk space. It's important to know the different error scenarios that could lead to this error message when you're troubleshooting your system. And 4, and this is something we'll get back to time and time again, all resources are finite. It may seem that nowadays we have a lot of disk space, but if it's possible to exhaust it, some process somehow will. A common Unix file system may seem to have near infinite number of files it can store, but the file system is restricted by the number of available inodes, and those can be used up too. We'll see many other examples throughout the semester. We'll also revisit a lot of what we touched upon here in the next couple of videos, but I hope that this warm-up exercise helped to get you thinking about file systems and the resources we're managing in this fashion. Make sure to check out links in the slides and read
Okay. So again, another thing that we need to consider, of course, is the moving an EBS volume across operating system. So I don't know if you're familiar with AWS, no, AWS, no, they will have, of course, some operating systems, no, wherein you could able to create instances, no, for given OS, either Linux man yan, FreeBSD, NetBSD, or OmniOS, no. So you could also able to create 1 GB volume and attach it to one of the instances, a new file system on the volume and mount it, and file on the new file system, and you could able to terminate the first instance, attach the volume to the second instance. So it can retrieve, of course, the file from the volume via the second instance. So what you're going to do is just repeat for a different OS, and we need to take note that any differences in the process or tools, can you use the same volume /file system across different OS instances. So the AWS instances or file system instances actually move an EBS volume across operating system. As what I mentioned earlier, even you are using Linux, FreeBSD, NetBSD, or OmniOS. So I just want to show you another presentation on how you'll be able to perform these file system exercises. Now, as what we have here, we have a command, the sudo mount -t uf, of course, ts, and of course, we have also cat/mnt file. Later on, I will show you or a demonstration on how you'll be able to perform this one using NetBSD actually, instance, And as what I mentioned, for us to understand this application specifically on how we'll be able to do these activities, in creating these AWS instances, creating 1 GB volume, creating new file system, create a file on the new file system, terminate the first instance, attach the volume to the second instance, and retrieve the file from the volume via the second instance. Please do watch this video.
the basic exercise in the hope that this will set you on the right track to then explore the other questions and dive a bit deeper into the topic at hand.
Actually, class, if you have a laptop or computers sa bahay o kaya dyan right now, No, I don't know if you have any schedule in the computer laboratory, if they have also Linux no applications. You will try no these demonstrations for you to, of course, to know on how you'll be able moving an EBS volume across different operating systems. Kung mayroon lang naman po.
The exercise itself is intended to get you familiar with the concept of cloud storage and to visualize how we can use elastic block store volumes just as if they were hard drives that we plug into a physical system. So let's see how we do this. Let's start by creating two instances. In the easier example, you create two instances of the same OS, but later I'm going to ask you to try two different operating systems to illustrate the requirement for file system support. Then we create a new volume and attach it to one of the instances. We create a file system on the new disk and mount it, and write a file to the file system. Then we can terminate the first instance. Now note that any files stored on the root file system of this instance are lost to us, as they are not persisted anywhere. But since we're looking at our custom volume here, we are then still able to attach this volume to the other instance now, and then retrieve the files from the volume via the second instance. Pretty straightforward, right? But this gives you an opportunity to practice the commands relating to file systems and disks. But I bet you picked your favorite operating system for this exercise. So why not make it a little bit harder on yourself and pick an OS that you're not as familiar with? You should find similarities, but some of the tools will behave differently, or you may need to use different tools altogether. And next, the more interesting question is, can you do this with two instances that do not run the same OS? That is, can you mount a disk with a file system created on one OS on another OS? Let's give this a try. So let's start with a NetBSD instance. And an Ubuntu instance. Now, to create a volume, I have another shell function to avoid me having to type too much. It's called new volume, and it takes two optional arguments. That is, if a first argument is given, it should be the size of the volume in gigabytes. If a second argument is given, it would be the availability zone. If neither is specified, we default to 1 gig volume in US East 1A. There. Now, we attach this volume to a NetBSD instance. This one up here. Next, we SSH into the instance. And look at the dmesg output for our disks. There we are. XBD0 as the root disk, XBD1 as the newly added disk. We use the disk label tool to look at the partition table, which is shown here as a default, with a single partition spanning the whole disk. So let's create a new file system on this disk. We use the default UFS file system version 2. And mount it under /mount. There we go. Next, we create a file on the file system. So, we can now unmount the disk again. And exit. We then detach the volume from the instance and unceremoniously terminate our running NetBSD instance. Now, Let's see what the instance ID was of the Ubuntu instance we started. There it is. So let's now attach the volume to this instance. And SSH to that instance. Here we are. Let's use the ls-block command to show the disks it uses here. And there it is. Now we mount this disk. But since this disk contains a file system that's not the standard file system on Ubuntu Linux, we have to specify that this is a UFS file system, and we specify the version as well. The Linux kernel only supports UFS in read-only mode, so we specify that mount option too. And there's the file we had previously created on the NetBSD instance. And there you have it. We successfully moved the volume from one EC instance of one OS to another instance of another OS, and were able to access the files. As I said, please give this a try and make sure you understand all the commands used here. Then repeat the exercise using different operating systems and see if you can go the other way, creating a file system on, say, Linux and mounting it on FreeBSD, for example. Some of the links here may be useful for you in the process. If you run into problems or have any questions, don't hesitate to ask on the mailing list or in our class Slack.
Okay, so we need to understand that these are always full. It is futile to try to get more disk space. So data expand to fill any void, of course. So no matter how much storage you allocate, your user will find a way to use it up. So we need to think about how to try to avoid the perpetual state of full, no? So this will be for discussions about the core concepts, no? We have the basic desk concepts, no? Storage, no? We have basic file system concept and file system, of course, no? So within each of these topics, no, we have a few subtopics. So in order to understand basic these concepts, no, we need to take a look at common storage model, which is the primary topic later, no, in the video presentation or demonstration. Following that, we'll talk a bit about this interfaces, no? This interface, that's what we have here, no? We need to understand how we connect storage devices, both physical as well as what protocols we use, no? We'll talk about physical aspect at the same time, no? Wherein we could able to know the important and understand file system concept as what video presentation later will show, no? And from there, we will talk about partitions, no? Which will flow logically from the discussions of the physical structure, no? So then within the area of file system concepts, no, we'll talk about how to combine storage devices using, for example, no, a redundant array, no, of independent disk or RAID, no, yung RAID. So logical volume management and how formatting devices may influence the storage capabilities. And finally, the video presentation later will talk about what you can do with storage media once you have it hooked up appropriately. Now, what types of file system there are and exactly how the traditional Unix file system works. And this part will be covered, of course, with a discussion. So we distinguish, no, different storage models by how the device in the charge of keeping layers, no, keeping the bits in place, no, interacts with the higher layers by where raw block devices access is made available by where a file system is created to make available to the disk space as useful unit. So by which means and protocols the operating system accesses the file system. Somewhat simplified, and we identify the operating system. The storage device itself, let's say for example, the thing where the bits are actually stored, and the file system sitting on top of the storage device and interacting with the application software. So the first and most common as well as most simple storage model we'll talk about here is the direct attached storage. No? It's just, of course, what it sounds like. The storage medium most commonly, a physical hard drive is directly attached to the host. No, if you look at your laptop, no, or a workstation, or a desktop, or a physical server, you likely find a physical hard drive present. No, so one partition on the physical disk, yung /dev /this one mounted under slash, as well as several other partitions mounted elsewhere in the file system. Now, for a workstation or a typical server, no, the direct attached, no, storage device might be a regular IDE hard drive, as the one, of course, as later, no, we will show in a video presentation. And on the right, we will see how the different components come together, as obvious as it may be seen. So the storage device is part of the physical server and managed by the operating system. Again, the file system is created on the storage device and facilitates access to the block level storage provided by the hard drive to the application software on the file level. No? So makes sense now, right? Now, direct attached storage is a very simple architecture with a number of advantages. Now, since there is no network or other additional layer in between the operating system and the hardware, the possibility of failure on that level is eliminated. Likewise, a performance, no, penalty due to network latency, for example, is impossible. No? At the same time, there are some disadvantages. Since the storage media is well directed attached, it implies a certain isolation from other systems on the network. And this is both an advantage as well as a drawback. No? On the other hand, each server requires certain data on the private or unique to each operating systems. On the other hand, data on one machine cannot immediately be made available to other system. But we frequently want to be able to access certain data from multiple servers. Now, when a user logs into host A, let's say, for example, he or she expects to find all his or her files in place, just as when he or she logs into host B. Recall that our shared Linux system at yung sa kay Steven discussion earlier, no, are behind a load balancer. So when SSH to Linux lab, no, may be dropped into one of the several physical system, but still expect to, and fortunately do, have all my files available. So the way we can accomplish this is by having the data, no, stored on a network attached storage devices, no, which sits on a central location somewhere, and where the file are accessed via, for example, as the network file system or NFS. Okay, so how does this work? No, we see that there is a central server, no, in this case, which offers the data from the directory. So from a specific path, and the local host, no, in this case, no, mounts that under /home / yung let's say kung ginamit natin na folder SG GS yung kanina kay Steven, no. So the file server, no, must have the actual storage and has created a file system on that, which it then makes available over the network, such that client can access it but these clients do need to support the network file system, which in turn provides the standardized abstraction of the file level access to the application software. We need to take note that the file server accesses the storage device as direct attached storage. Meaning, it's or as best as we can speculate anyway, meaning it's physically connected to that server. What that looks like in practice depends on the scale of the system. But seeing how the path, of course, is called yung X-RAID natin na 0-1, and just be an Apple X-RAID appliance, a mass storage device that was offered by Apple up until 2008 and which offered storage up to 10 terabytes or so. So we could remember that while this system is no longer in use, the export paths were kept the same to avoid having to update all possible clients, it seems, And of course, it is important, of course, to understand which, in fact, your regular house, yung instance will utilize an EBS volume as local storage. What we see, of course, is the volume that is attached as this under the /dev/SDA1. So we can get more information via the describe dash volume command, which give us the details about the volume size and some other properties. But with EBS, we can always make new disk magically appear. And we have 4 GB size disk actually. And now, as a block level storage device, we can directly write files to this, but would need to create a new file system. Something we'll get back in the recommended as what we discussed earlier. But for now, let us, of course, watch a video or a brief demonstration on how you'll be able to perform the EBS volume, moving EBS volume. So as what I mentioned earlier, this will be the storage devices. The storage model, Linux storage is based on the block devices. Block devices provide buffered access to the hardware, always allowing to read or write any size block, including single characters or even bytes, and are not subject to alignment restriction. They are commonly used to represent hardware like hard disk. We have also a direct attached storage, yung DAS na tinatawag natin. Direct attached storage refers to a data storage unit that is attached directly to a server or workstation. So an internal host bus adapter, yung tinatawag nating HBA, available in PCI Express or PCI DAS-X is required to connect a direct attached storage system via a cable that is usually no more than 5 meters away from the servers or workstation it is serving. So once the DAS unit is attached, it works as through the drivers are internally connected to the server or workstation to which it is connected. In Microsoft Windows, mas commonly ngayon, Windows 11 or any other compatible operating system will see the device as an internal device, which can then be partitioned and formatted just like any other internal hard drive or RAID array. So the Broadberry or CyberStore DAS is connected directly using the latest SAS. Ano yung SAS? Serial Attached SCSI technology. So the device is as fast and in most cases even faster than the drives that are already inside the server or workstation. So, the direct attached storage, so yung DAS na tinatawag natin, is a type of storage that is attached directly to a computer without going through a network. So, the storage might be connected internally or externally. Only the host computer can access the data directly. Other devices must go through the host computer to work with the data. Considering the high availability, high access rate due to storage area network absence, elimination of the network setup complications, storage capacity expansions, data security, and fault tolerance. So, the network attached storage, no, yung NAS na tinatawag naman natin, is a file level storage architecture that makes stored data more accessible to network devices. NAS is one of the three main storage architecture along with storage area networks and direct attached storage. No? NAS gives networks excuse a single access point for storage with built-in security, management, and fault-tolerant capabilities. Network attached storage can be set up as a container-ready storage option, essentially a setup where storage is exposed to a container or a group of containers. So containers are highly flexible in bringing incredible scale to how apps in storage are delivered. So, how does NAS work? No, in hardware, no, pre-configured storage software is installed on dedicated hardware known as NAS box, NAS units, NAS server, or NAS head. And this hardware is essentially just a server containing storage disks or drives, processors, and random access memory. For software, the main difference between NAS and general purpose server storage lies in the software because NAS software is deployed on a lightweight operating system that's usually embedded in hardware. Generally, purpose server have full OS that send and receive thousands of requests every second. So a fraction of which may be related to storage, while a NAS box sends and receives only two types of requests: data storage and file sharing. When it comes to protocols, no, yung NAS, no, a NAS box is formatted with data transfer protocol, which are standard ways of sending data between devices. So these protocols can be accessed by clients through a switch, which is a central server that connects to everything and routes requests. So data transfer protocol basically let you access another computer's file as if they were your own. So network can run multiple data transfer protocols, but two are fundamentals to most networks: the Internet Protocol, yung IP natin, and Transmission Control Protocol, yung ating TCP. No? TCP combines data into packet before they're sent through an IP. Think about TCP packet. No? I think you're familiar because you have networking 1 and networking 2. So TCP packets as compressed SEP files and IPs are IP as email addresses. No? If your grandparents aren't on social media and don't have access to your personal cloud, you have to send them vacation photos via email. Instead of sending those photos one by one, you can bundle them into zip files, no, before sending them over. In similar fashion, TCP combines into packets before they sent across networks through internet protocols. So the files transferred across the protocols can be formatted as network file system. Kanina nabanggit natin yung network file system or NFS. So this protocol is regularly used on Linux in Unix system. As a vendor agnostic protocol, network file system works on any hardware, operating system, and network infrastructure. Another is the SMB. Hindi siya San Miguel Corporation. SMB stands for Server Message Block. Okay? Most systems that use server message blocks run Microsoft Windows, where it's known as Microsoft Windows Network. SMB developed from the Common Internet File Sharing, yung ating CIFS protocol, which is why you might see it referred to as the CIFS SMB protocol. Kung kanina may SNB, meron tayong AFP. Okay, hindi siya yung AFP is an Apple filing protocol. So yung ating SMB for Microsoft Windows, yung ating ginagamit naman sa Apple is or Mac OS is AFP, no, Apple Filing Protocol. This will be a proprietary protocol for Apple devices running on Mac OS. So we have of course some benefits, no, of the NAS, no, or SAN, no. So scaled out capacity, no, performance, easy to set up, no? Accessibility and fault tolerance. So, how about NAS versus clouds, no? NAS by itself is not a cloud. No? Clouds are IT environments that abstract, pool, and share scalable resources across a network. NAS can be an important part of the cloud environments, particularly when cloud providers deliver storage to client as part of the infrastructure as a service or yung yung tinatawag nating AAS, no, agreement. So storage area networks provides block storage, no? So the block storage, no, split storage volume like hard disk, virtual storage nodes, or pool of cloud storage into a smaller volume known as blocks, each of which can be formatted with different protocols. Diretso na lang tayo para mas maaga tayo matapos, okay lang ba? Kasi kung magkakat pa tayo, no? Okay. So, it can be formatted with different protocols. Let's say, for example, one block can be formatted for NFS. Another can be formatted for AFP. And a third can be formatted for SMB. This gives users more flexibility, but also makes navigating the blocks harder since they bundles data together using arbitrary classifications, no? And we have also direct attached storage, no? And software-defined storage. When it comes to cloud storage, no? So we have the first level, the Dropbox, G Drive, iCloud. The object level, actually we have AWS S3, no? The block level is AWS SBS, no? The cloud storage models are model of cloud computing that stores data on an internet via cloud computing providers. And these providers manage and operate data storage as a service, no? Cloud storage is basically an online storage on data, no? Data that is stored can be accessed from multiple connected devices, which constitute a cloud, no? So we had, of course, the virtual disk in the cloud, no? But of course, hard drives, that instance storage run on the physical attracted to the EC2 host, which are running the store, their endurance depends upon the lifetime of the instances attached to them. So yun yung mga advantages and disadvantages ng cloud, no? Actually, pag sinabi nating cloud, meron tayong tatawag na web scale NAS, no? Okay, so this time I'll just want you to, of course, there is a certain discussions and actually this will be a demonstrations of the storage model disk, particularly for a continuations of the discussions as what I have here earlier.
System Administration. This is week 2, segment 1, and we're going to be talking about storage models and disks. As system administrators, we are responsible for all kinds of devices. We build systems running entirely without local storage, just as we maintain the massive enterprise storage arrays that enable decentralized data replication and archival. We manage large numbers of computers with their own hard drives, using a variety of technologies to maximize throughput before the data even gets onto a network, just as we often require and guarantee access to shared data storage across the internet. We begin with this topic because without data storage, we can't even bring up an operating system. We are always dealing with ways to store data, and so as a sysadmin, we better have at least a rough idea what's involved here, what can go wrong, and how to scale data access. Talking about scaling data storage, that's really a futile endeavor. No matter how much we make available, we'll soon run out of it. Think about it. Just a few years ago, having access to even just 1 gigabyte of data was mind-boggling. Alright, for most of you, this probably has shifted, and the notion of needing a terabyte of storage for your videos, photos, and music doesn't seem so outlandish. But of course, you may also have heard the famous quote attributed to Bill Gates that 640K ought to be enough for anybody. Data expands to fill any void. No matter how much storage you allocate, your users will find a way to use it up. So we need to think about how to try to avoid the perpetual state of full disks. For that, we will discuss the following: basic disk concepts, basic file system concepts, and file systems in general, as well as the traditional Unix file system in particular. Within each of these topics, we have a few subtopics. In order to understand basic disk concepts, we need to take a look at common storage models, which is the primary topic of this video. Following that, we'll talk a bit about disk interfaces, how we connect storage devices both physically as well as what protocols we use. We'll talk about physical aspects of disk drives, as they are important to understand file system concepts later on. And from there, we'll talk about partitions, which will flow logically from the discussion of the physical structure, as you will see. Next, within the area of file system concepts, we'll talk about how to combine storage devices using, for example, a redundant array of independent disks, or RAID, logical volume management, and how formatting devices may influence the storage capabilities. Finally, we'll talk about what you can do with storage media once you have it hooked up appropriately, what types of file systems they are, and exactly how the traditional Unix file system works. That part will be covered in the next week, while we'll try to cover all the other topics in week 2. So let's get started. We distinguish different storage models by how the device in charge of keeping the bits in place interacts with the higher layers, by where raw block device access is made available, by where a file system is created to make available the disk space as a useful unit, by which means and protocols the operating system accesses the file system. Somewhat simplified, we identify the operating system, the storage device itself, i.e. that thing where the bits are actually stored, the file system sitting on top of the storage device, and interacting with the application software. Okay, so the first and most common, as well as most simple storage model we'll talk about here is Direct Attached Storage, or DAS. That's just what it sounds like. The storage medium, most commonly a physical hard drive, is directly attached to the host. If you look at your laptop, a workstation, a desktop, or a physical server, you'll likely find a physical hard drive present. Here, we see one partition on the physical disk, the fdisk1, mounted under /, as well as several other partitions mounted elsewhere in the file system. Now for a workstation or a typical server, the direct attached storage device might be a regular IDE hard drive, as the one shown here. On the right, we then see how the different components come together, as obvious as it may seem. The storage device is part of the physical server and managed by the operating system. The file system is created on the storage device and facilitates access to the block-level storage provided by the hard drive to the application software on the file level. Makes sense, right? Direct attached storage is a very simple architecture with a number of advantages. Since there is no network or other additional layer in between the operating system and the hardware, the possibility of failure on that level is eliminated. Likewise, a performance penalty due to network latency, for example, is impossible. At the same time, there are some disadvantages. Since the storage media is, well, directly attached, it implies a certain isolation from other systems on the network. This is both an advantage as well as a drawback. On the one hand, each server requires certain data to be private or unique to its operating system. On the other hand, data on one machine cannot immediately be made available to other systems. But we frequently want to be able to access certain data from multiple servers. When a user logs into host A, she expects to find all her files in place just as when she logs into host B. Recall that our shared Linux systems at Stevens are behind the load balancer so that when I SSH to Linux Lab, I may be dropped into one of several physical systems. But I still expect to, and fortunately do, have all of my files available. The way we can accomplish this is by having the data stored in a network-attached storage device, which sits in a central location somewhere, and where the files are accessed via, for example, as shown here, the network file system, or NFS. Okay, so how does this work then? We see that there's a central server, Kronos.SourceIT, in this case, which offers the data from my home directory, from a specific path, and the local host, Eva in this case, mounts that under home Deschaume. So the file server must have the actual storage and has created a file system on that, which it then makes available over network, such that clients can access it. But these clients do need to support the network file system, which in turn provides a standardized abstraction of the file-level access to the application software. Now, note that the file server accesses the storage device as direct attached storage, meaning it's, as best as we can speculate anyway, physically connected to that server. What that looks like in practice depends on the scale of the system. But seeing how the path on Chronos.SourceIT is called xRAID 0-1, it might just be an Apple xRAID storage appliance, a mass storage device that was offered by Apple up until 2008, and which offered storage of up to 10 terabytes or so. I remember when I worked here at Stevens back in 2006, we did buy an xRAID and used it as our NAS. While this system is no longer in use here, the export paths were kept the same to avoid having to update all possible clients, it seems. I also have a little sysadmin war story relating to this xRAID here at this link for your entertainment. Anyway, now network-attached storage allows multiple clients to access the same file system over the network, but that means it requires all clients to use specifically this file system. The NAS file server manages and handles the creation of the file system on the storage media and allows for shared access, overcoming many limitations of direct attached storage. At the same time, however, and especially as we scale up, our requirements with respect to storage size, data availability, data redundancy, and performance, it becomes desirable to allow different clients to access large chunks of storage on a block level. To accomplish this, we build high-performance networks specifically dedicated to the management of data storage, storage area networks. In these dedicated networks, central storage media is accessed using high-performance interfaces and protocols such as Fibre Channel or iSCSI, making the exposed devices appear local on the clients, appearing effectively as a block device using direct attached storage, as shown here on the right. Another chunk carved out from the storage pool could then be used by a separate file server to build a new file system on and export that via NFS, as illustrated here on the left. Storage area networks are also specifically that, networks. That is, they can be configured in a true switched fabric using hardware that looks a lot like network gear, where it may use a variety of protocols to overlay storage communications on existing networks or build brand new separate networks, often using fiber optical connections. Now, once you've internalized that the SAN may be a fully switched fabric and can be used to make available both flexible block-level storage as well as file-level network storage, it comes as no surprise that you end up with yet another layer of abstraction and start to offer storage as a service in, what else? The cloud. Now here, there's yet another set of distinctions that we want to make. 1. Services that provide file-level storage and access, as in the case of file hosting services, such as, say, Dropbox, Google Drive, or Apple iCloud. 2. Services that provide access on an object level, hiding file system implementation details from the client and providing for easy abstraction into an API, with Amazon's Simple Storage Service, or S3, being the prime example. And 3. Services that offer clients access on the block level, allowing them to create file systems and partitions as they see fit, such as, obviously, AWS Elastic Block Store or EBS. All of these categories have one thing in common. In order to provide the ability of accessing storage units in a programmatic way, they offer a well-defined API for access, oftentimes HTTP or REST-based. On the service provider side, shown here in the bottom of this graphic, the storage model in use remains an opaque system to the customer. They may use a storage area network to combine large numbers of distributed storage resources to present a large storage pool to the users. As users of the system, we really don't care, and the storage magically appears, as if out of the blue. We have already and will continue to see how this works by using AWS, but let's quickly illustrate the distinction between the object level and block level. First, let's take a look at S3. We create a new S3 bucket, and then recursively copy a bunch of files into it. And that's it. Nothing else needed. It really couldn't be much simpler. Just like that, we backed up a directory full of files into cloud storage with the ability to inspect the contents via the command line and without having to worry about whether there is enough storage available, how large our files are, or whether there are any limitations on how many files we can create. Pretty neat, huh? Well, let's nuke those files again. Goodbye. All right, next, elastic block storage. As the name suggests, this cloud storage method allows for access on the block level, meaning we get a device that looks and behaves just like a real disk. From an instances perspective, this is really just a variation of direct attached storage, because the virtual machine doesn't know nor care where the block device comes from. And in fact, your regular AWS EC2 instance will utilize an EBS volume as local storage. As shown here. What we see here is that we have a volume that is attached as a disk under def SDA1. We can get more information via the describe volumes command. Which gives us the details about the volume size and some other properties. But with EBS, we can always make new disks magically appear. Here, let's create a new 4 GB size disk. Now, as a block level storage device, we can't directly write files to this, but would need to create a new file system, something we'll get back in a recommended exercise in just a minute. But for now, let this brief demo suffice to illustrate what cloud storage can look like. Alright, let's take a break here and recap what we covered. We distinguished 4 primary storage models: direct attached storage, or DAS, network attached storage, or NAS, storage area networks, or SAN, and cloud storage. We noted how these can be combined and may offer different kinds of access, although we primarily distinguished between block level access, where the device appears as if it was a directly attached physical disk, and file level access, where systems interact with a storage medium through a file system or API. Each of these models has a number of implications. For starters, it's important to remember that even when we're dealing with magic storage appearing out of nowhere in the cloud, somewhere somebody is managing a physical storage medium. Secondly, as we add layers of abstraction and allow for increased flexibility, we are changing the security model. A directly attached physical drive can only be compromised from that host or by physical access, but a network file server may be.
So, as I mentioned earlier, no, SCSI, or pronounced SCSI, no, and sometimes colloquially known as SCSI, no. So the Small Computer System Interface is a set of American National Standards Institute, no, standard electronic interfaces that allow personal computers to communicate with peripherals hardware such as desk drives, tape drives, CD-ROM, drivers, printers, and scanners faster and more flexibly than previous parallel data transfer interfaces. So, although not all devices such all level of SCI standards are generally backward compatible. No, that is, if an older peripheral device is attached to a newer computer with support for a later standard, the older device will work at the older and the slower data rate. In personal computing, no, the SCSI interfaces have been replaced for the most part by, of course, yung USB natin, no? Universal Serial Bus. in the enterprise, SCSI is still used in server farms for hardware drive controllers. No? So there are several components used in SCI storage systems. No? Number one, initiator. No? An initiator issues requests for service by the SCSI device and receives responses. So initiators come in a variety of forms and may be integrated into server system board or exists within a host bus adapter. So ISCSI connectivity typically uses a software-based initiator. Okay. Another is the target. No? A SCSI target is typically a physical storage device, although software-based SCI target also exists. So the target can be a hard disk or an entire storage array. It's also possible for non-storage hardware to function as SCI target, although rare today. It was once common for optical scanner to be attached to computers through the SCSI bus and to act as the SCSI target. No? Another is the service delivery subsystem. Okay? The mechanism that allows communication to occur between the initiator and the target, it usually takes the form of cabling. We have also expander, no? Only used with serial attached SCSI, yung SAS na tinatawag natin, allows multiple SAS devices to share a single initiator port. The next, of course, is SAS products are compatible with devices that employs earlier SCSI. So the serial storage architecture standard can be used when SCSI performance is not adequate as an ISCSI, which preserve the SCSI command set by embedding SCSI-3 over TCP/IP. SAS has become a popular alternative to parallel SCSI in enterprise environments. No? Wait, accept. So it support up to 65,535 devices through the use of expander. So the latest parallel SCSI, wait. Okay, so as I mentioned earlier, SAS support up to 65,535 devices. So the latest parallel SCSI standards allow for only 16 devices because it eliminates issues with terminations and clock skew. It is a point-to-point technology. This means SAS is not subject to the resource contention issues that are so common with parallel SCSI. So, another is the ATA. I think everybody familiar with ATA. Ano nga yung ATA? ATA stands for? Sige nga. Somebody? ATA stands for? Okay, pakitype na lang. ATA stands for Advanced Technology Attachment. It is the standard physical interface for connecting storage devices within a computer. So ATA allows hard disks and CD-ROMs to be internally connected to the motherboard and perform basic input-output functions. ATA is also known as, ano yung ginagamit natin sa programming, also known as Integrated Device Electronics, yung IDE, and it is referred to as ATA with packet interface or yung ATAPE, no? We have also SATA, no? SATA is the full serial advanced technology attachment, also called serial ATA. So, an interface for transferring data between a computer's central circuit board and storage devices. SATA replaced the long-standing PATA, yung parallel ATA interfaces. So, the ATA interface standard was designed to connect supported integrated and portable storage devices without the need for an external controller, no? Because the ATA interface is basically a set of thin wires merged within a cable bus that are used to transfer data in and out of the disk drive. Initially, ATA actually supported parallel communication and was called parallel ATA o yung PATA nga na tinatawag, no? It consider of a 40-pin controller cable and data transferred speed of 16 to 32 bit, no, at a time. So however, parallel ATA was replaced by serial ATA, no? So which has transferred data input output speeds in computer system developed from, actually that is way back 2007, no, onward. So the original ATA, no, specification defined one dual channel, no, ATA interface that supported one or two ATA devices. So, meron tayong tatawag na ATA 1, ATA 2, no? So ATA 2 defines a second interface with the primary interface using standard ATA IRQ, no, and base address, and the secondary interface using the alternate IRQ and base address that had always been set aside for the purpose. So any modern motherboard or interface card provides dual ported ATA support, no? So meron tayong Windows NX, NT, 2000, XP, and Linux recognized and use the secondary interface automatically. So syempre, ang operating system automatic may DOS, no, may internal commands, no, and 16-bit Windows are not dual port ATA aware. So installing more than 2 ATA drives with these operating systems required either BIOS support for the secondary port or supplemental drivers, no? So if BIOS setup allows you to enter drive parameters for 4 drives, you already have the BIOS support you need. If BIOS setup lists only 2 drives, you must, no, actually in order of desirability, install an updated system BIOS or use a dual ported bus mastering ATA adapter with an onboard dual port BIOS or install dual port device driver. So in addition, in the well-standardized primary and secondary ATA interfaces, some devices support semi-standard tertiary and quaternary or quaternary ATA interfaces. So in theory, at least you can support up to 8 ATA devices on one computer by adding a dual ported interface card that can be configured as tertiary or quaternary to a system that includes a standard dual ported ATA interfaces. Assuming that you have the 4 IRQs needed to support all 4 ports, no? We have not seen a BIOS that includes direct support for ATA ports 3 and 4. Although the current Phoenix BIOS specification allows ATA port beyond 1 and 2 to be defined arbitrarily, no? And we have, of course, the IDE, as I mentioned, no? So IDE or IDE interface is an industry standard for connecting IDE devices, enabling them to communicate with each other. So at one time, most computers included at least one IDE interface built into the motherboard. So the interface provider provided a 40-pin connector for attaching an IDE hard disk drive, no, to the computer. So Digital combined the hard disk and controller card into one unit, thereby inventing IDE. Early IDE devices actually use expansions card, no, called a paddle card, but this card was not really a disk controller, no. It simply provided an interface between the bus and the embedded disk controller on the hard drive itself. All modern systems had IDE interfaces embedded on the motherboard. And actually, you may not you may or may not need to understand much about IDE to install and configure a hard drive, depending on how old your hardware is. The most recent drives, motherboard, and BIOS handle the hard parts for you, automatically detecting and configuring the drive interface and BIOS for optimum performance. So if all you're doing is installing a new IDE hard drive in a recent PC, you can safely skip this entire discussion. Now, if however you're upgrading an older system with a new drive, installing an older drive in a new system, or installing an additional drive, accept. Okay? Component is more than a few years old. No? So you need to understand quite a bit about IDE, not just to configure the PC for optimum performance, but also to ensure that your data is not corrupted by running data transfer rates higher than your hardware can safely support. So understanding the fundamentals of IDE also helps you make good decisions when you purchase drives, boards, and add on IDE interface card. No? Although IDE was originally proprietary, yes, no, the cost and performance advantages of IDE quickly made it in the standard hard disk interface. No, by 1990s, most computer system came with IDE hard disk. No, a slew of acronyms and standard has arisen as IDE proliferates. Now, some meaningful and many that are just marketing hype. No. Next will be the SSD. So a solid state drive, no? That ano ba yung SSD? SSD is a solid state drive, no? It is a storage device that uses integrated circuit assembles to store data persistently, no? Typically using flash memory and functioning as secondary storage in the hierarchy of computer storage, no? Speaking of SSD, the form factor is a key specification. There are plenty of form factors for SSD, and within about 5 years of mass market mainstream adoption, many SSDs were already held, backed by comparatively slow data rates available for hard drives. Unlike hard disk drives, no, some SSDs are limited by maximum throughput of SATA. No? So we have also fiber channel, no? So it is a high-speed data transfer protocol that provides in order lossless delivery of raw block data. It is designed to connect general purpose computer, no, mainstream and supercomputers to storage devices. And this technology or the technology primarily support point-to-point, no? Ibig sabihin, two devices directly connected to each other. Though most common found in switch fabric, no, device connected by fiber channel switches environments, no. We have also of course an applications, no, the SAN, no, and the storage protocols, no. Okay, so storage protocol or network protocols provides a standard set of rules that define how data is transmitted between devices. So, systems such as NAS, no, and storage or SANs rely on storage protocols, no, to facilitate data communication. So, the emergence of network storage has allowed organizations to decouple their server and storage purchasing decision. Thus, multiple application database server can share storage on the same network attached storage server or on a block storage controller via storage area network protocol. So this is unlike direct attached storage system where these are connected to an application, to a database server. So in DAS environments, even if one only needs to add more storage, one has to also add more servers. Now, various types of storage network protocols has emerged actually to support NAS and SAN systems. So currently, the same storage boxes, no, can support both distributed file NAS protocols such as NFS, CIFS, and block storage area such as ISCI and FCP or yung fiber channel. So this will be an example of a storage protocol bit rates, no, as what we have here. So we have the technology, the rate, and the year, no? So from 1963 to 1980. So the single disc, no? We have the 18 TB, no? And of course, this will be for the disc device configuration using a single disc. GBOD, no? So GBOD stands for just a bounce of disk. Just a bound of disk. This will be a type of multi-level configuration for this. No, it refers to a collection of disks in a computer system or array combined as one logical volume. So JBOD is used by organizations that need an efficient on-premises storage method. So it drives our individual drivers, meaning that each drive in your system is seen by computer as an individual disk volume. So it drives allows you easily add additional storage to your system. Just connect another drive and allows for easy to manage and less expensive backup solutions. Okay, so meron tayong RAID, nabanggit ko na ito kanina. Redundant Array of Independent Disk. No? It is a way of storing the same data in different places on multiple hard disks or solid state drives, no, to protect data in the case of drive failure. So the best RAID configuration for your storage system will depend on whether you value speed, data redundancy, or both. So if you value spend most of all, choose RAID 0. So if you value data redundancy most of all, remember that the following drive configurations are fault tolerant. So why is RAID used? RAID stands for Redundant Array of Independent Disk, and combines multiple hard drives together in order to improve efficiency. Depending on how your RAID is configured, it can increase your computer speed while giving you a single drive with a huge capacity. So RAID is extremely useful if uptime and availability are important to you or your business. Backups will help ensure your from a catastrophic data loss, but restoring large amounts of data, like when you experience a drive failure, can take many hours to perform. Meron tayong RAID 10, no, is the fast and safest of all choices. It is the fast and safe. The obvious downsides are the RAID 10 has less storage capacity from the same disk and is more costly on the basis of capacity. It must be mentioned that RAID 10 can only utilize an even number of disks, as these are added in pairs. We have, of course, a single disk. So this configuration contains the settings that Windows uses a partition and to configure one or more physical hard disks. Now, valid disk partition configurations can vary depending on whether you are using a BIOS-based computer for a unified extensible firmware interface-based computer. So to set up a new hard drive with raw space on Windows 10, use, of course, some steps. No, number 1, open start, search for create in format hard disk drive, accept. Partitions, and click the top results to open the disk management console. You need to right click the hard disk, no, drive marked as unknown and not initialized, and select the initialize disk option. Another is the flash array, no. An all flash array or AFA, also known as solid state storage disk system or solid state array, is an external storage array that uses only flash media for persistent storage, no. Flash memory is used in place of the spinning hard disk drive, yung HDD natin, or a group of physical devices or drives that is used to define logical volumes or devices. An array is a type of MD or M disk that is made up disk drive, and this disk drive are members of the array. Okay, so this will be a total discussion of a device and interfaces.
Hello, and welcome back to CS615 System Administration. This is week 2, segment 2, and after we covered conceptual storage models in a previous video, we'll next be talking briefly about storage devices and interfaces. As usual, this is merely scratching the surface on a much larger topic, but I hope you get a bit of a taste of the many layers and concepts involved as we talk about storage media. Let's begin with SCSI, one of the older standards describing how to connect devices or peripherals to computers and transferring data between them. The Small Computer System Interface has been around for over 30 years and exists in a confusing number of implementations and variations. SCSI used to be the default method to connect any peripheral device using long, wide, and generally unwieldy ribbon cables and different types of connectors. Here's a SCSI drive, but different devices may use different connectors and require different cables. SCSI has now largely been obsoleted by the Advanced Technology Attachment or ATA standards, but still lives on in the iSCSI standard, specifying storage connections using the SCSI command protocol over IP-based networks, a common choice in storage area networks. Another variation we'll see in a few minutes is the modern Serial Attached SCSI, SAS, or SCSI over Fiber Channel protocol. The ATA standard, on the other hand, is often equated with the Integrated Device Electronics Interface, or IDE. You may have seen parallel ATA using flat wide ribbon cables that make it impossible to wire multiple drives inside a server case, although nowadays, fortunately for sysadmins in their hands, serial ATA or SATA is more common. These are your typical hard drives, which are named Integrated Device Electronics because the drive includes the controller, integrating some of the complexity carried on the motherboard and separate controller and SCSI. That is, the drive includes a controller circuit as well as a few bits of firmware to facilitate the access. Now, we're talking about a fairly low-level connection here, but now is as good a time as any to remind you that security affects everything. A few years ago, it became public that the NSA was capable of implanting malware in the firmware of hard drives, which included an API and the ability to read-write arbitrary information into hidden sectors on the disk. This is a really difficult threat to protect against, and a good reminder of the fact that just about anything can be compromised. Specifically, it helps us consider that words have meaning, and that the name Integrated Device Electronics implies that there is not just a bit of rather helpful magic sitting there. But don't fret, not every hard drive is necessarily compromised, and you are not necessarily likely to be on the target list of the NSA. However, for several reasons, including security, but more likely performance, you may wish to move away from IDE drives, perhaps towards solid-state drives, or SSDs. An SSD drive puts away with having mechanical rotating magnetic platters on which to store data, and instead uses integrated circuits to store data persistently, such as flash memory. These drives are significantly more resistant to physical shock, more silent, and have less latency than IDE drives, which is why your cell phone most likely uses SSD for storage. While still more expensive than traditional mechanical hard drives, you nowadays find more SSD or flash memory in use even in the server market. These will still use the SATA standard to connect, but may also be combined into larger storage devices, which then might be connected externally or over a storage area network, using, for example, the Fiber Channel protocol. Fiber Channel is usually used in the switched fabric, meaning it looks and behaves a whole lot like your normal switched Ethernet network, and utilizes optical fiber cables, shown here on the top right, although you can also run it over copper wires. Now, if all these different technologies are not enough for you, you also want to consider that in just about any but the most simple environments, all of these are combined in some form when storage area networks are created. That is, you will likely find a multi-layered stack of protocols, building on top of the Fiber Channel protocol, which might be utilized in a pure optical Fiber Channel network, an Ethernet network on top of regular TCP/IP, and so on. Similarly, the SCSI protocol may be used on top of either one of those, or over something like remote direct memory access over, say, InfiniBand. That is, we have all sorts of means to piggyback storage protocols on top of other protocols. ATA over Ethernet, for example, allows us to reuse our existing Ethernet network and turn it into a storage area network by encapsulating ATA frames into Ethernet frames. Fiber channel over Ethernet is the same, but for the fiber channel protocol, and thus gives you an idea, a trend whereby folks realize that, hey, we already have a working network here, let's just make it carry block level instructions as well. So you really get anything over Ethernet, which makes things quite easy, but also notably implies that the storage area network you build in this way is restricted to the same layer 2 network segment, and as it runs on that layer, has no inherent security properties. So you can then try to push things up the stack by using, for example, iSCSI, which includes authentication and can be wrapped in IPsec, for example. And of course, we can take it up a notch and move on to serial attached SCSI, which we mentioned earlier, and which nowadays is used in huge storage arrays, such as this one, offering efficient high-speed storage access using the SCSI commands and protocol on modern hardware. But true to its SCSI heritage, SAS of course also suffers from no shortage of confusing variations and connectors. As you can tell, the opportunities to broaden your understanding or to specialize in storage technologies and protocols are not limited in any way. As a quick look at how technologies have advanced, note how performance throughput has increased over time and by protocol. You see all the technologies we mentioned so far in the scroll, increasing bit rates over time. Noting the introduction of fiber channel with around 100 megabyte per second, and then moving forward with the various over Ethernet variations. Now going over gigabit Ethernet and eventually over 100 gig Ethernet, which is really pretty slick. So this addresses the bit range for throughput. But just how many bytes can we store on the different media? Well, the individual IDE drive has come a long way from the roughly 5 megabyte drive costing around $1,500 in 1980, hasn't it? I remember well when we built servers with 500 megabyte drives, when eventually a 10 gigabyte drive was considered huge, but of course nowadays that's nothing.
You've got the idea. GoDaddy has the domain to make.
In fact, the price of storage for IDE drives has gone down so much that you can now buy an 18 terabyte drive for just about $600. 18 terabyte in a single IDE drive. That's just amazing. So yeah, in a way, upgrading your individual disk drive is an example of scaling vertically, as we discussed in the previous video. But even if 18 terabyte is not enough for you, because, as we established, disk usage expands to fill all available space, you can consider just getting a whole bunch of them and hooking them up one by one. That'd be a disk configuration commonly referred to as a JBOD, just a bunch of disks, which is exactly what it sounds like. You'd buy a bunch of drives, and there you go. Now there's a fair bit of overhead on your server, because you have 15 individual disks, but it's certainly an approach that might represent horizontal scaling, with all its implied drawbacks. Or perhaps a better approach might be to take all of these beefy Exos drives and put them into a RAID controller to then combine them into a single volume, in effect combining the vertical and the horizontal scaling approaches. We'll talk a bit more about RAID in our next video, but of course nothing requires us to use IDE drives for this approach. We could instead use SSDs, right? Like this one. This is a 100 terabyte solid state drive. 100 terabyte in a tiny 3.5 inch form factor. Only problem? This will cost you a cool $40,000. Yep, you heard that right, $40,000 for a 100 terabyte SSD. Well, SSDs are more expensive, but they also are a lot faster and reliable than HDDs. So talk about scaling vertically here. And now imagine scaling that horizontally as well into a storage appliance that combines SSDs or flash memory like this NetApp all-flash arrays shown here. Again, as you can see, there are countless ways to combine things to provide you with the right solution for your storage needs, with each carrying its own advantages or disadvantages. And so there's no single simple solution to say, you should buy X or you should use Y. What the right solution is depends on your specific requirements as well as we've just seen, your budget. Sky's the limit. Okay, I think we're going to take a quick break here. Next time, we're going to be talking a bit more about RAID and logical volume management, as well as the physical aspects of a typical HDD. But before we go there, I'd like to leave you again with another exercise. Let's pretend you're a sysadmin working at Stevens, and you have to replace the current storage system we use for the home directories on Linux Lab. What solution would you propose? Now, obviously you're lacking a lot of information to make this call, but on the other hand, you can probably make an educated guess on the storage needs based on the observed usage. Try to spec a solution and then see how much that will cost you. Then consider that as an academic institution, you are likely bound by a budget with certain limitations. Finally, consider what implications your choice might have on the rest of the compute environment. Okay, I think this should keep you busy until the next video. See you then. Cheers.
So I think that's it for today. So we'll already finish now the discussion about the disk driver. This will be our lesson number 2, no, module number 2, the storage models and disk. So this coming Wednesday, we have an activity. No, gagawin po natin, mag-join lang kayo. I-share ko sa screen yung activity ninyo. Tapos kung meron kayong mga question, pwede kayong mag-raise ng question doon sa Wednesday. No? So, next Monday, what we're going to discuss is the file system basic and the software types. No, this will be focused actually more on the system and storage models, file system forensic analysis, and software installation and package management. So our topic for next meeting focus on the BOST process and the MBR, no, the file systems, the Unix file system, and files go yung here na ano natin. Okay? So I think that's it for today. So looking forward that you will be able, of course, to be on Wednesday for our first quiz. Okay? So thank you for attending our class and good morning.